Hello, my name is Jed Murdoch, and welcome to Module 10 on effective population size. In this module, we'll cover the idea, the concept of effective population size. We'll also run through a variety of ways in which you can calculate effective population size. A little bit later, my colleague Terry will join us, and she'll build a spreadsheet and walk you through a spreadsheet exercise that will demonstrate those calculations, which I think will also give you a better understanding for what this idea of effective population size means. So with that said, let's begin. In earlier modules, we've covered a lot of issues related to the genetics of a population. And perhaps one of the foundational concepts, one of the foundational issues that we covered is that of the Hardy-Weinberg principle. And the Hardy-Weinberg principle, if you recall, is simply that if we assume a population is quite large and that population undergoes random mating, and not only that, there are no selective pressures on that population. So in other words, we don't see natural selection or mutation, we don't see gene flow in fact, that the genotype frequencies, the genetic makeup of that population will really remain consistent from one generation to another. Now, oftentimes we consider these Hardy-Weinberg populations to be ideal. So sometimes they're referred to as being ideal populations. And there are also a couple of other things, a couple of other assumptions that we make about them. One of those assumptions is that these ideal populations have an even sex ratio. In other words, there's an equal number of males and an equal number of females in that particular population. We also assume that the reproductive output of individuals is the same. In other words, each individual is contributing equally to the next generation with respect to their genetic material. And we also assume that the population is really unchanging, so it's pretty consistent. It doesn't fluctuate very much over time. So how does this relate now to real populations? If we consider like bison or rattlesnakes or dung beetles or something like that, any sort of population that's real, how does that relate to our notion of an ideal population, which is really a benchmark by which we make comparisons and statements about the state of real populations? Well, in reality, most real populations violate at least some of the assumptions of what we expect under ideal circumstances, under the notion of an ideal population. So real populations rarely match ideal populations. Consider your favorite species. Just think about that for a moment. Mine happens to be the African wild dog. African wild dogs violate many assumptions of Hardy-Weinberg. For one, or these ideal populations, for one, we know that sex ratios are quite different. So among populations, very detailed studies of African wild dog ecology have found that there are imbalances in sex ratios. There's slightly more males than females, and that might be due to the inherent risks of dispersal that are a little bit stronger for males than females. What else do we know? We know that wild dogs in Africa are a packing species. They live in these social groups, packs. Packs have several adults. And in most circumstances, we have a dominant pair that does most of the mating. Not all, but most of the mating. And so with respect to reproductive output, it's very skewed, it's very uneven. So we've got some individuals that are producing a lot more than others. And then lastly, if you think about African wild dogs, they are an endangered species. So they live mostly in eastern and southern Africa in very discrete populations, populations of relatively small size. So they're not very large populations, and because they're quite small, we see that they go through various fluctuations. So a real population of African wild dogs is not ideal, really, in any sense. So the question is, how do we characterize real populations? How do we characterize these real things? How do we characterize a population of, let's say, cheetah, right? That may be existing out there, especially from a genetic perspective. We can certainly characterize them in other ways, but from a genetic perspective, how do we characterize them? And one way that we do that is by estimating this thing called effective population size for a given population. Now, a textbook example, or definition, I should say, of effective population size is that it is the size of an ideal population that would lose genetic material at the same rate as our population under consideration. Now that sounds a little strange, a little complicated. So let's just walk through a couple of examples that I think will make it a bit clearer. So let's now consider a population of cheetah, for example. And let's say we've been dispatched to the Serengeti and we've had the opportunity to study cheetahs in the wild. And we go out and we survey a population and we estimate that there's, let's say, 270 cheetah in this system, which is a pretty good number. That's a pretty decent number of individuals. But let's say we've calculated the effective population size of that larger population. And that effective population size is 50. So our real population is 270, but our effective population is 50. What that really means is that our 270 population is behaving genetically as though they're an ideal population of 50. So I'll say that again. A population of 270 here is behaving as though it's a population size of 50. So it's behaving such that its genetic makeup is changing as though it's an ideal population of 50. So these ideal populations, again, we assume there's random mating. We also assume that there's an even sex ratio, that there's even reproductive output, and that there's really no population changes. But a slight departure from Hardy-Weinberg is that these smaller populations, right, any sort of finite population will experience some genetic loss. And that would be through things like genetic drift, which we talked about in earlier modules, and through inbreeding as well, right? So genetic drift can result in the chance, it's a random process that can result in the chance loss of alleles from a population. And of course, inbreeding can reduce heterozygosity in a population. So again, we've covered those in previous modules. So any finite population will experience those. And so if we have a population of 270, but it's behaving like a population of 50, an ideal population of 50, we see that that ideal population will probably be losing genetic material a lot faster, right, due to genetic drift and also due to inbreeding. So we may think that our population of 270 is in good shape, but in fact, from a genetic point, it may not be quite as strong as we expect. So again, we're making characterizations about our larger population from a genetic point of view. Now, if you think about effective population size and you review some of the studies out there, you find that basically most real populations have very different effective population sizes. In fact, effective population size tends to be about half, sometimes less than half, of our real total population size. So if you think about a real example of cheetah in the Serengeti, the effective population size of a current population of cheetah there is about 44% of that total population. Now, if you consider another large cat example, if we go now to Nepal and you look at the tiger population in Royal Chitwan National Park, you find there that effective population of tigers, of the population there, the effective population size is about 40% of the total population. So quite a bit smaller. So what affects effective population size? What are some influences that have impacts on effective population size? Why do we see this discrepancy between effective population size and real population size? Well, for one, changes in the population level from one year to the next can have an influence on the genetic nature of a population and thus affect effective population size. So changes over time in a population can have an influence. We know from real populations, African wild dogs, for example, there are changes in population level from one year to the next. We don't have this consistent population that's the same. Sometimes those swings are quite significant for some species. Occasionally we see really wild, extreme changes in population level. We've seen among cheetah and other species like bison, for example, these bottlenecks. In other words, we've had a large population that's been heavily reduced down to a very small number of individuals. And then from that small number of individuals, the population is then expanded to a large number. In other words, the population has gone through this genetic bottleneck in which the whole new population has spawned from a small amount of genetic material, a small number of individuals that pass through this little bottleneck, so to speak. And as you can imagine, when these bottlenecks occur, that can have tremendous influences on the genetic nature of that population. So these kinds of fluctuations, extreme fluctuations, certainly can have an influence on effective population size. So let's look at an example. Let's say we've transported our operation, our cheetah operation, from the Serengeti down to Namibia, for example. And we've gone out and we've surveyed cheetah and we've found that there are 1,000 in this population. And then we surveyed them again sometime later and we find that there's only 10 individuals in the population. And then we survey them again and we find that there is in fact 1,000 again. So here we have a case of a bottleneck. 1,000 going down to 10, expanding out to 1,000. So that's quite an abrupt change. This is a hypothetical example and may be beyond the sort of capabilities of cheetah, but nonetheless, just imagine that for a moment. So this new group, our current population, right, is much more closely related to each other because of that bottleneck than the initial 1,000. And because of that, it's genetically very different. So we expect a much lower effective population size. And so for our group of 1,000, the actual effective population size is 29. Very small. So the point being here, even though we've got this big population that we think is in good shape in terms of numbers, from a genetic perspective, it's behaving as though it's an ideal population of 29. So that ideal population will be losing some genetic material, some diversity rather, through processes like drift, and there may be greater incidences of inbreeding that can reduce heterozygosity. And that might be a real concern. The loss of genetic diversity from a population can have some red flags in terms of conservation. For one, genetic diversity tends to have beneficial effects for populations because it gives them the ability perhaps to adapt to uncertain situations in the future. There's also a conventional notion that lower amounts of genetic diversity have consequences for the fitness of individuals. And that certainly is true for some species in some circumstances, but just as a caveat, that's not always the case. But nonetheless, if we have a large population that's genetically behaving like a really small population, we need to be somewhat concerned about that because, again, we could have these losses in genetic diversity. So it's a good measure of the state, perhaps the genetic health of a population. So I've run through two quick examples here, right? Our Serengeti cheetah population and given you a number there of 50 as an effective population size. And we've run through an example in Namibia in which the effective population size was 29. So hopefully at this point you're asking yourself, well, how the heck do I calculate effective population size? So for a fluctuating population, one that's changing over time, and we've got some estimates of that population change, let's run through how you might calculate effective population size. So how did we arrive at our estimate of effective population size for our last example? I told you it was 29. So we surveyed, of course, cheetah 3 times. And in our first survey, we had our population being 1,000 individuals. In our next survey, it was 10, quite a big drop. And then in our last survey, it was 1,000. So we've had a changing of fluctuating population size. And I told you for our population of 1,000 that our NE, our effective population size, was 29. So how do we calculate that? Before I do, let me also just or explain it rather, let me also just note that effective population size is usually denoted as N with a little subscript here, E. And this is the form you might see it noted as in literature and publications and also in textbooks. So what is our effective population size? How do we go about calculating it? Well, one way that we do that, and this is a common way, is to calculate something called the harmonic mean. Harmonic mean, and I'll write it out here. The harmonic mean is a term you might recall from long ago, right, from your early days of taking math courses. A harmonic mean is a type of average. And we know there are lots of different averages out there. Well, not lots, but there are a few. We're used to the basic average, right, which is you sum your values and you divide by the number of values. That's an easy one. We use that all the time, and it's good when you have discrete numbers. There are other types of averages. There's something called the geometric mean, which is good for like investments and calculating values for mean values for area, for example. There are a variety of uses for geometric means. But then there's this harmonic mean. And the harmonic mean, again, it's a type of average. And this is the average that you would use for those dreaded standardized test questions. And you probably remember this one, right? So imagine you are in New York City and you're taking a train, and that train travels all the way to Los Angeles. There we are, going 30 miles per hour. You remember this one? And then on the way back, it travels 60 miles an hour. And so the dreaded question was, what is the average rate of travel? Well, we can't really use an arithmetic mean here. We can't use our standard measure of average. And part of the reason for that is that we have our initial journey being really half the speed of our second journey. And so if we actually calculated the arithmetic mean, we'd get a value of 45. And that's just not really the correct answer, because again, in the first leg of our journey, we're just not going nearly as fast as we are in the second leg of our journey. So harmonic means are really good at estimating averages for these kinds of problems in which you've got some rate. So you've got 2 units here, you've got 1 unit of travel in this direction, 1 unit of travel here. And so the harmonic mean accounts for the fact that you're going much slower during this rate than you are during this rate. So in some ways, when we're dealing with effective population size, we're kind of like dealing with rates. We're saying, well, in our first period, our first year, our first generation, we have kind of a rate of our population. So our population is genetically this size for that period. And then in our second period, we have kind of like a rate again. We've got a small number of individuals, and then again, we've got our population expanding again. In this case, we're kind of treating these as though they're like rates for different periods. And the harmonic mean is really good because it accounts for these smaller values, and to state it simply, it sort of gives them a little bit more weight. Now, if we want the equation for harmonic mean, which hopefully you're asking, if you want to solve that question about going from New York City to Los Angeles, this is the basic equation for a harmonic mean. It's the number of your units divided by the reciprocal of each of your values. And so the reciprocal is just 1 over your value. So for our ongoing journey, our journey to Los Angeles, during that particular unit, we went 30 miles an hour, right? And then in our second unit, we went, on our way home, we went 60 miles an hour. So if we want to solve this equation here, we've basically got 2 units divided by the sum of the reciprocals. And that then should give us a value of 40. And that's the correct answer. So remember, the arithmetic mean gave us a value of 45. When we're estimating effective population size for a fluctuating population, we essentially do the same thing. We calculate the harmonic mean. And this is a general equation that we might use. So our effective population size is T. This is the number of time units now, number of years or generations or another measure of time unit, divided by the reciprocal of each one of our measurements summed together. So this is the harmonic mean, and that gives us a little bit more weight for those smaller populations, which then gives us a better measure of what we expect our effective population to be. Now, I should say that the equation you see here is oftentimes written a little bit differently in the literature. And we oftentimes see it written this way, as, again, another reciprocal. And we'd multiply that then by the sum of our reciprocals. So in this case, we'd have n1 plus n2 plus ... all the way out to nt. So if we estimated effective population size using this equation and this equation, they basically will give us the same answer. But this is a form that you'll see oftentimes in textbooks. So we'll use that to estimate effective population. And now for a new population. So let's forget about our 29 thing here for a moment, and let's calculate it for a new population. You can calculate that one on your own. So for a new population here, let's say we estimated our cheetah here in 6 different time periods, and we want to know what's the effective population size for our most current measurement. So when the population's at 1,000 in our 6th year, let's say, what is the effective population size? So in order to do that, we will put our equation up here. That's a t. And then we've got, of course, 1 over each one of our values summed together over nt, right? So what does that give us? 1 over t, how many t's do we have? We've got 6 periods, right? And in this case, we have 1 over 1,000. This gets a bit long, so my writing will be a bit small. Over plus 1 over 5 plus 1 over 5 plus 1 over 1,000 plus 1 over 5 plus 1 over 1,000. I can just barely get it on here, but I think you get the point. It's the sum of the reciprocals of all of our values. And so 1 divided by 6 gives us a value of 0.167, I think, if I've done the math correctly. And this whole expression here should give us the value of 0.603. And remember, we're dealing with the reciprocal of NE here. So to solve for NE, we do a little cross multiplying, and we should have NE now being 1 divided by this multiplied by this, which, if I've done the math correctly, is 0.1, which means that our effective population size here is 10. Okay, so even though we counted 1,000 individuals during our last survey, genetically the population is behaving as though it's an ideal population of 10 individuals. Make sense?